Welcome students to our third lecture on the design of different components of drop spillway. We have already discussed in the previous classes what is the design discharge including the freeboard. So, in this lecture we will be talking about how to design the different components using the hydraulic principles. Basically, to design the drop structure, three aspects are more important. First is to estimate what is the design discharge. The design discharge is a function of L, H, and if you are considering the freeboard, then F also accounted for. You can see this equation Q equal to C L H to the power 3 by 2 divided by 1.1 plus 0.03 capital F. We are using this equation when the freeboard is considered. That means, for freeboard we are providing an additional discharge of 0.1 plus 0.03 F times Q. So, that is your excess discharge which is provided as the freeboard. Then another thing we have to consider that for economical section, small h divided by capital L and small h divided by capital F should be less than 0.5. If small h divided by capital F is greater than 0.5, then it will invite more scouring. For this, generally we use small h divided by capital F is less than 0.5. So, I have to select a combination of L and small h such that these criteria are fulfilled. This figure shows the left side view of the drop spillway. The different components are listed in the slide. You can see that the value of T and C, the cut-off wall and toe wall, the depth of cut-off wall and toe wall is provided as it should be minimum should be 1.2 meter. This value is provided generally to avoid any piping failure of the hydraulic structure. The longitudinal and end seal is given as small h divided by 4 and S, that is your height of transverse seal, is equal to DC by 2. DC is your critical flow depth. This figure shows the top view of the drop structure. You can see the wing walls are provided at 45 degree from the vertical, and these are having a slope of 2.828:1, and other dimensions are given in this figure. For estimating the different components of this drop spillway, first you have to estimate the critical depth, because generally after the drop there is a possibility of hydraulic jump, and we have to estimate critical depth. In this case there is no submergence flow, there is no tail water here. So, DC equal to estimated as DC equal to Q square divided by L square G whole to the power 3 by 2. You know already this from this hydraulic principles. Then the height of transverse seal is estimated as half of this DC value. Height of head wall HB is estimated as F plus S. You can see from this figure F plus DC divided by 2. Height of head wall extension is equal to F plus S plus H, that is given by equation number 4. The minimum length of head wall extension is given by these two equations 5 and 6, which is estimated as 3 into H plus 0.6 and 1.5 into F. Among these two values, the maximum value is selected for designing of E, which is nothing but the head wall extension E as marked in this slide. Similarly, the minimum length of apron is estimated as f into 2.28 into small h divided by f plus 0.52, and you know that the small h divided by f is always less than 0.5. The height of sidewall and wing wall at the junction is given by j. You can see from this figure, this is j, that equal to 2h or f plus s plus h minus 0.5 into LB plus 0.1, and the maximum value of these equations 8 and 9 is selected for designing the value of j. Similarly, the depth of toe wall, you know that the depth of toe wall or cutoff wall should be minimum 1.2. So, that is why I have given here, you have to select in between 1.2 and 1.65 into s plus 0.4 f plus 0.75 divided by 4. Then the sidewall dimension, that is m, as marked in this figure, is estimated as 2 into f plus s plus h minus j, and we can estimate the value of k as LB minus m, because LB equal to k plus m as shown in this figure. So, I have given in this table the total summary of the different components of this drop spillway, and all these components are given here. Simply you can use this table to estimate the different parts of this drop spillway. So, whatever we have summarized, it is DC equal to q square divided by g L square whole to the power 3 by 2, height of transverse seal that equal to DC by 2, height of head wall that is given by f plus s, f is known already, height of head wall extension that equal to f plus s plus h, minimum length of head wall extension is given by the maximum value among 3 h plus 0.6 and 1.5 f, minimum length of apron is given by f into 2.28 into h divided by f plus 0.52, heights of sidewall and wing wall at the junction is given by the maximum value in between 2 h and f plus s plus h minus 0.5 into LB plus 0.1, and the depth of cutoff wall and toe wall is selected in between 1.2, that is the minimum value, and 1.65 into s plus 0.4 f plus 0.75 divided by 4. The sidewall dimension is given by 2 into f plus s plus h minus j, and the sidewall dimension k value is given by LB minus m. So, this table summarizes all these components which can be designed by knowing the value of q, the length of wear, then depth of wear, that is small h, and the drop, that is your capital F. This is one example. By if you will solve this example, many things will be clear about the design. Suppose the spillway discharge is given as 7 cubic, this is the design discharge, total fall is given as 3 meter, the discharge coefficient C equal to 1.84, which is for rectangular wear. There is free flow condition, that means the hydraulic jump is allowed. So, you can estimate the value of DC. Now, you have to perform the hydraulic design. Before going for design, our first approach is that we have to select the value of L and H such that it will meet the criteria of Q, that equal to C L H to the power 3 by 2 divided by 1.1 plus 0.03 F, which accounts for the freeboard also. So, it is given. So, by using this equation, you can select in between small h and capital L such that small h divided by L and small h divided by F both are less than 0.5, and after assuming these small h and L values, you can estimate the value of Q, that is your revised design discharge, such that this revised estimate of Q is nearly equal to 7 cubic. Now, coming to the selection of small h and L values. So, here I have assumed the value of L at the first instant as 5.6 and small h equal to 0.75. Since C equal to 1.84 and f equal to 3. So, I can estimate the value of small h by L that equal to 0.13, which is much less than 0.5 and it is as per my design criteria, and the value of small h divided by f is coming to be 0.25, which is again as per my design criteria, which is less than 0.5, and my estimated value is 5.6, which is estimated by using this equation, but this value is much lower than that of my design Q value, that is your 7 Q mech. Then finally, I have selected L equal to 5.8, H equal to 0.85, and correspondingly I am getting small h divided by L as 0.15, small h divided by f equal to 0.28, and both are less than 0.5, and I am getting the value of Q as 7.03, which is nearly equal to 7 Q mech, which is my design discharge. So, from this table I can estimate that the value of L equal to 5.8 meter, H the depth wear is 0.85 meter, and the design Q is 7.03 Q mech. Now, by using these values I have to go for the computation of different components. I can use the summary table, or I can go step by step also. So, first thing I have to estimate what is my critical depth, because it is a free flow condition. So, the critical depth is estimated as 0.06 meter. Q is known, L is known, and G is 9.81. So, by using those values, known values, I can estimate what is the critical depth, that equal to 0.06 meter. Then the height of transverse shield DC by 2 will be equal to 0.03 meter. The height of head wall is given by F plus S. So, that you can see from this figure. So, F plus S equal to 3 plus 0.03. So, the total fall is 3 meter. So, that is known. So, you will get 3.03 meter. The height of head wall extension is given by F plus S plus H. So, that is equal to 3.88 meter, and the minimum length of head wall extension, that is given by E. So, I have to select between the maximum between 3 H plus 0.6 and 1.5 F. By putting the values of H of 0.85 and F of 3 meter, I can get that 3.15 value and 4.5. So, I have to select in between 3.15 and 4.5. So, my maximum value is 4.5 meter. So, the value of E equal to 4.5 meter. Now, the minimum length of apron, that is your LB. So, that is given by F into 2.28 into small h divided by F plus 0.52. The value of H is 0.85, F is 3 meter. So, by using these two values, the minimum length of apron is estimated as 3.5 meter. Similarly, the heights of side wall and wing wall at the junction, that is equal to J. As you can see from this figure, this J value is estimated by considering the maximum value in between 2 H and F plus S plus H minus 0.5 into LB plus 0.1. So, LB is already known, that is 3.5 meter. So, this value I have put here, and small h, F, S and H are known. So, by that calculation I could estimate two values, that is 1.70 and 2.10. So, among these two values I have to select 2.10. So, my J value is 2.10 meter. Similarly, the depth of cutoff wall or toe wall is given by the maximum value among 1.2 meter, because that is my minimum value as per the design considerations. and 1.65 into S plus 0.4 F plus 0.75 divided by 4. So, by using these values I have to select in between 1.2 and 0.82. Naturally 1.2 is the maximum value. So, I am getting C equal to T equal to 1.2 meter. Then the sidewall dimension, the M value can be estimated as 2 into F plus S plus H minus J. So, that equal to 3.56 meter. Then the value of K can be estimated as L B minus M. So, that equal to 3.5 minus 5.6. So, this is coming to be negative. Negative values are not allowed. So, you can take it approximately 0. So, that completes my first question. Now, coming to the second example, this is slightly different from the first example. So, here you have to design one drop structure under free flow condition. The catchment area of the gully is given as 50 hectare. The maximum rainfall intensity is given as 12 centimeter per hour, which is occurring once in 50 years of return period for the period equal to the time of concentration of the catchment. That means, the design intensity is given as 12 centimeter per hour of rainfall. The drop of bed is 2 meter. You have to take the value of C, that is the discharge coefficient for the rectangular wire as 1.84. Assume a runoff coefficient of 0.35 for the catchment. The site conditions are such that the length of the wire crest should be within 4.5 to 5.5 meter. That means, L can be selected as 4.5 to 5.5 meter. So, in this case the value of Q is not given, the design discharge is not given. So, for that you have to estimate what is the design discharge. So, the design discharge can be estimated by using the rational formula, which gives the design peak rainfall runoff. So, the design peak runoff can be estimated by using the formula Q equal to K I A, where K is the runoff coefficient, I is the design rainfall intensity, which is given here 12 centimeter per hour, and A, that is your catchment area, that is equal to 50 hectare. Once Q is known, then we can follow the procedure whatever we adopted for solving the example number 1. Now, we have to go for solving the problem, and here the drop is given as F equal to 2. The drop of bed is 2 meter. So, drop F can be equal to 2 meter. So, we can use the rational formula here. If you use the rational formula, Q equal to K I A, K is given 0.35, I equal to 12 centimeter per hour and A equal to 50 hectare. So, by putting these values after unit conversion, you can get the value of Q as 5.83 cubic. So, my design discharge is 5.83 cubic. So, once Q is known, I can design my drop spillway. I have to use this formula Q equal to C L S to the 3 by 2 divided by 1.1 plus 0.03 F, and it has already accounted for the freeboard. So, now I have to select the best combination of L and H, so that H by L and H by F both are less than 0.5, and L is in between 4.5 to 5.5 meter depending on the site condition. That means, I have to select first L within 4.5 to 5.5 meter. I can start my trial from 4.5 and I can increase L value up to 5.5 meter. So, first I have taken the value of L as 4.5 and the assumed value of small h equal to 0.8. I am getting small h by L as 0.18, which is less than 0.5. Small h by F is 0.4, and my estimated Q by using this equation is 5.11 cubic, but my design discharge is 5.83 cubic. So, I have to increase the design discharge, that means, I have to select higher L value. If you will see, I have taken L equal to 5 meter here, then L equal to 0.82, then I am getting small h by L as 0.16, small h by f equal to 0.41, and correspondingly I am getting q equal to 5.89 by using the above equation. So, this is approximately, not approximately, but it is approximately equal to 5.83 q mech. So, I can select this value as my revised q value, the design discharge value. So, finally, I got L equal to 5 meter, H equal to 0.82 meter, and my design discharge q equal to 5.89 q mech. Now, I can fill up the table, the summary table, by using the value of L, H, Q and F as given here. So, these values are already known. So, by knowing these values, I can put these values to estimate my critical depth, that equal to q square divided by g L square whole to the power 3 by 2. So, I am getting 0.053 meter. Similarly, S equal to d c by 2. So, I am getting 0.027 meter, H b 2.027 meter, H e that I can get 2.847 meter, E I have to select in between the maximum value of 3 into 0.82 plus 0.6 and 1.5 into 2. So, I am getting this value as the maximum one. So, that is I am getting 3.06 meter. The length of the apron, that is L b, I am getting 2.910 meter, and the value of j equal to 1.640 meter. The depth of toe wall and cutoff wall is given by C and T. So, I am getting the maximum value among these two. So, I am getting it is 1.2 meter. Similarly, the value of M is 2.410 meter and value of K is 0.750 meter. Simply you can follow the steps whatever we have discussed in our previous example. So, I am not going into details about this tables how to calculate. So, all these steps are already done in the example number 1. Now, coming to the third example, this is again slightly different from the previous two examples. So, here you have to design the drop spillway considering the frequency analysis by using the probability distribution functions. The question is that design a drop spillway for free flow condition for a return period of 20 years for an area, assuming that the data follows extreme value type 1 probability distribution. The extreme value type 1 probability distribution nothing but your Gumbel distribution. The mean and standard deviation of flow are 7.6 q mech and 6.3 q mech. So, the mean and standard deviations are given. The drop of bed is 3 meter, that means F is given as 3 meter. The side condition is such that the length of wire crest should be in between 7 to 9 meter. So, that means L should be selected in between 7 to 9 meter. So, my first attempt will be to decide what is your Q value, design Q value, which is having 20 years return period. So, for that I have to use the Gumbel probability distribution, and for that I have to use the mean and standard deviation values whatever given as 7.6 and 6.3 q mech. This equation shows the Gumbel probability distribution function. In this case, Q t is my design discharge value having a return period of t, here t equal to 20 years, and that is given as beta plus alpha into y t. Here alpha equal to sigma into square root of 6 divided by pi. So, sigma is nothing but it is the standard deviation, that is given as 6.3 q mech. Beta is given as mu minus 0.577 alpha. So, mu is given as the mean value. So, mean value is 7.6 q mech and alpha is already computed in the previous step. So, once alpha is known, I can estimate what is the value of beta. Then y t is called as the reduced variate So, that is a function of the return period. So, that can be estimated as minus ln of ln into ln of t divided by t minus 1. So, here t is 20 years. So, once y t, beta and alpha is known, I can use these values in this equation q t plus q t equal to beta plus alpha y t to estimate my design discharge. So, here the values of alpha is computed as 4.9101, beta is computed as 4.7659, y t is estimated as 2.9702 because t is 20. So, by using these three values alpha, beta and y t, I can estimate my design discharge which is equal to beta plus alpha y t. So, that I am getting as 19.35 qmec. So, this 19.35 qmec is my design discharge. So, once this design discharge is estimated, then we can use the simple procedure whatever we have already done in the previous examples. So, I have to use this equation q equal to C L h to the 3 by 2 divided by 1.1 plus 0.03 f. F is given as 3 meter and C is equal to 1.84, and I have to again follow the same condition, that is small h divided by L is less than 0.5, small h divided by f is less than 0.5 and L is should be selected, that is within 7 to 9 meter. So, L should be within 7 to 9 meter and my design discharge is 19.35. That means, I have to estimate the value of L and H in such a way that my estimated Q value is nearly equal to 19.35 qmec. So, I can use this table. So, I have started my assumption from L equal to 7. So, if I am using L equal to 7 and H equal to 1.4, then I am getting H by L equal to 0.2, H by F is 0.47 and both are less than 0.5, and my estimated Q value is 17.93, which is much less than that of my design Q value, that equal to 19.35 qmec. Now, I have to increase the value of L, so that the Q value will increase. So, if I have taken L equal to 8 meter and H equal to 1.35 meter, then I am getting H by L equal to 0.17 and H by F equal to 0.45, and my estimated Q value by using the above equation is 19.40 qmec, which is nearly equal to 19.35 qmec. So, my revised design discharge is now 19.4 meter and the value of L equal to 8 meter and value of H equal to 1.35 meter. So, now by knowing this small h, capital L and design discharge Q, I can now design my drop spillway by using the summary table. So, all these calculations are given in this table. So, by using these values of L, H, Q and F are shown in the right hand side here, I can estimate my DC, that is the critical depth of flow. So, that equal to 0.464 meter, S equal to DC by 2. So, that equal to 0.232 meter, HB equal to 3.232 meter, HE equal to 4.582 meter, E is estimated as 4.650 meter, minimum length of LB equal to 4.638 meter, J equal to 2.7 meter and C equal to T, they are both as 1.2 meter, M equal to 3.764 meter and K equal to 0.874 meter. So, all these steps, whatever steps we have already done for solving example number 1, those steps can be followed. So, those steps I am not repeating in this slide. So, this completes the example number 3. So, today what we did, so we have design the components of drop spillway, and for that we have to know what is my design discharge. Corresponding to my design discharge, I have to select the value of small h and capital L, such that small h divided by capital L and small h divided by capital F both should be less than 0.5 to avoid any scouring, and the value of L should be selected depending on the practical site condition. And for designing discharge, I have to use the formula Q equal to C L H to the power 3 by 2 divided by 1.1 plus 0.03 F, and this already has accounted for the freeboard condition. So, that means the freeboard, for freeboard whatever the extra discharge is given, that has been accounted for, and the value of this extra or additional discharge for freeboard is Q times 0.1 plus 0.03 F. So, by knowing all these values, we can use in the summary table whatever I have given to estimate all these components of the drop spillway. So, this ends our lecture here. Thank you.